Greetings, everyone. Thank you for listening in on my talk. My name is Daniel Wilson. I'm a PhD student at Liberty University, working under Dr. Wayne Strasser. And today I'm going to be talking about smart atomization, how we implemented PID control in a biosludge atomizer. So first, I want to talk about two challenges facing our modern world: waste management and energy demands. There's an ever-increasing production of human waste. This waste often includes toxic elements that lead to serious environmental and health hazards, making waste management a major global concern. Additionally, ever-increasing energy demands and scarcity of resources drive the major need for alternatives to conventional energy production. Underneath these challenges lie an exciting opportunity: conversion of human waste to usable energy for an efficient optimization of resources. There are several ways that this is currently done. I'm not going to talk about these in depth, but they're digestion, gasification, pyrolysis, and have various disadvantages, including long waits, dilution, and drawing operations that make them less efficient than they could be. So the question is there a better way? We believe that there is, and it's this: direct spray injection of highly concentrated biosludge into a boiler for combustion. So let me break that down. The biosludge is just the term I'm using for human waste sludge. The boiler is our energy harvesting equipment, and we spray or atomize the biosludge as we inject it into the boiler to provide a higher surface area to volume ratio for better drying and combustion. The advantage of injecting a concentrated biosludge is that we increase the conversion efficiency compared to those other methods I mentioned, reducing water usage and fossil fuel emissions, and better addressing energy and waste management issues. Critical to this, of course, is effective atomization of the viscous biosludge, or getting small droplets. But another difficulty arises because the viscosity of the biosludge varies widely. If the viscosity gets too high, it can create a large pressure drop that restricts the flow of biosludge and leads to poor atomization quality, or large droplets. So we need an injection system that can self-correct as the biosludge viscosity varies. This leads to our objective: a smart atomization system that can effectively process highly concentrated biosludge with dynamically varying viscosity. When I say effectively process, I'm talking about two things: maintaining a consistent droplet size to protect atomization quality for combustion, and maintaining constant biosludge pump requirements to supply system reliability. Our approach is implementing proportional integral derivative, or PID control algorithms in CFD simulations of a biosludge atomizer. So this involves CFD modeling of the atomizer, incorporating two PID controllers in our CFD model, an initial proof of concept test of our smart atomization system, and preliminary assessment of mesh refinement and atomization characteristics. You can see our atomizer design on the right there. It's a twin fluid atomizer with steam as the assisting gas. Steam shear leads to biosludge instabilities and droplet formation. And the steam is helpful in that it reduces the biosludge viscosity, leading to better atomization, but it should be noted that the steam can also reduce boiler efficiency. We have two PID controllers that we add to the system, and recall that a PID controller just changes one variable to keep something else constant. So the first controller is a biosludge flow controller. We'll call that C1. This automates the flow of biosludge based on pressure drop. And the objective here is to maintain constant biosludge pump requirements for varying viscosity. Second, we have a steam flow controller. We'll call that C2. This automates the flow of steam based on droplet size. Our objective is to maintain atomization quality for varying viscosity. And we build a CFD model of this atomizer for our controller proof of concept test. You can see a side view of that there on the right, with biosludge is red, steam is blue, and you can see the droplet formation or atomization there. Now, this is for a proof of concept test. So our goals are model stability and sufficiently resolved biosludge droplets for controller testing, not necessarily super accurate droplet sizes to study the details of atomization. And our settings for this CFD model are largely based off of my advisor's many years of experience with CFD atomizer models. So we use a 1/32nd wedge model with periodic boundary conditions and an unconventionally coarse mesh with no grid independence, again, for a proof of concept. We use ANSYS Fluent for our solver and standard K omega turbulence model, simple PV coupling scheme, second order upwind for momentum, Presto for pressure, first order upwind for turbulence, Plick for VOF, time step of 2e-7, max of 7 iterations per time step, and our Courant number stays around 0.5. We implement the PID controllers as user-defined functions, or UDFs, in ANSYS Fluent. Okay, so we built our CFD model, and then we went to test the controllers through a 100-fold increase in biosludge viscosity. So we increased viscosity, just a step change from 0.05 to 5 kilograms per meter second. This is at a normalized flow time of 0 in the plots you'll see on the upcoming slides. Before the viscosity increase, all the tests only use C1 as kind of a constant baseline, and then we step increase the viscosity and evaluate 4 scenarios. No controllers, just C1, just C2, or C1 and C2 as a coupled controller system. Recall that C1 is the biosludge flow controller and C2 is the steam flow controller. So what did we find? Well, here we have the pressure plot on the left and the sludge flow plot on the right. It turns out that if we have no controllers, the pressure, this is equivalent to pressure drop, increases by 150%. That's red in the plot. If we have just C2, the pressure increases by 320%. That's the magenta there. But if we have C1 in our system, the biosludge flow decreases and the pressure returns to set point. So we conclude that C1 is necessary to maintain a constant biosludge pump requirement. What about the droplet size and steam flow? Well, here we have SMD, or solder mean diameter, which is our droplet size on the left, and on the right, our steam flow. So if we have no controllers, the solder mean diameter increases by 40% through the viscosity change. If we have just C1, the SMD increases by 20%. But if we have C2 in our system, the steam flow adjusts and the SMD returns to set point, concluding that C2 is necessary to maintain atomization quality. And if we look at all these results, then we see that we demonstrate the efficacy of the coupled controller system and demonstrate the need for both C1 and C2, not just one or the other. Next, we did a mesh refinement study, and to do that, we used 3 additional models. We took a 90-degree wedge base model, which had the same coarseness as the controller test mesh, and we refined that twice to get Ref 1 and Ref 2, which you can see at the bottom of your screen. And you'll notice that atomization characteristics remain relatively unchanged as the mesh is refined. The droplet sizes do decrease. We get smaller droplets with finer meshes, but overall the characteristics remain similar. So we conclude from this that the base mesh is sufficient for a smart atomization controller proof of concept. In other words, if the controller system works or doesn't work on the base mesh, then it probably will work or not work on a more refined mesh. And we can observe some other characteristics of the atomization system with our refined meshes. So here's a short animation of the biosludge being atomized. And you can see it's coming out in bursts. There were a couple little bursts there. So the interfacial unsteadiness leads to a pulsing flow, which amplifies the growth of instabilities and leads to better atomization. The time scale of these macro biosludge pulsations is on the order of 0.001 seconds. We can look at a still shot with this side view here, and right there is this radial burst event happening where the biosludge is swinging or pushing radially outward and breaking up. We can also look at droplet size. So if we look at our biosludge being atomized there again, it's clear that the droplet size is decreasing as you move axially away from the injector. And we can plot this as axial SMD profiles for each of the mesh refinement levels. A couple observations from this are that, one, Ref 1 and Ref 2 show successively lower droplet sizes, which we saw in the pictures on the previous slide. And each curve has roughly the same shape except for the humps in the lower two. These are just because the models haven't reached quasi-steady state yet. And finally, droplet sizes for Ref 2 are not half of Ref 1. So it seems that we're approaching mesh independence, or could be there already. We conclude then, or confirm our previous conclusion, that the general atomization characteristics are preserved through the various refinement levels. In conclusion, our objective is a smart atomization system to effectively process biosludge with dynamically varying viscosity. Our motivation is conversion of human waste to usable energy, addressing major global issues of waste management, resource optimization, and alternative energy production. Our valuable contributions are showing that a coupled controller system maintains relatively constant atomization quality and biosludge pump requirements for a 100-fold increase in biosludge viscosity, and that refined meshes generally maintain atomization characteristics, so our coarse mesh is sufficient for the proof of concept. In the future, we'd like to do more mesh refinement analyses and model the biosludge as non-Newtonian and include energy effects. That concludes my talk. Thank you so much for your attention. I appreciate it and would be happy to answer any questions you have. Thank you.